Good morning. Today we are going to discuss the vapor pressure of liquid solutions. Vapor pressure of liquid solutions. When I say liquid solution, the solvent is liquid and the solute can be a solid, liquid or gas. And here we are going to discuss liquid solute dissolved in liquid solvent. So we are going to discuss vapor pressure of liquid solute dissolved in liquid solvent. Now, the vapor pressure. What do you mean by the term vapor pressure? For this, let us consider a system in which a liquid is dissolved in liquid and it's a closed system. We know that after some time, the liquid will evaporate and change into vapor state. Now, after some time from the vapor state, the vapors will condense and go back into liquid state. And finally, the rate of evaporation and rate of condensation become equal. So we say that the system has attained equilibrium. And we know that the vapors present inside the container will exert a pressure. And we call that pressure vapor pressure. So the definition of vapor pressure is the pressure exerted by the vapor above the liquid surface in equilibrium with the liquid at a given temperature. Now, we can see that higher the temperature or weaker the intermolecular force of attraction between the molecules, higher will be the vapor pressure. So, vapor pressure is the pressure exerted by the vapors above the liquid surface in equilibrium with the liquid at a given temperature. Now, we have a law called Raoult's law for volatile liquids. That is, this Raoult's law relates vapor pressure with mole fraction for a liquid. And we have two cases to study. One is Raoult's law for volatile liquid. That is, both solute as well as solvent is volatile in nature. Volatile means they get evaporated fast. And the second case is Raoult's law for non-volatile solute. That is, the solvent alone is volatile, but the solute added is non-volatile. So next we are going to discuss Raoult's law for a volatile liquid. That means both solute as well as solvent is volatile. Raoult's law. For volatile liquids. Or we can also say Raoult's law for liquid solutions. Now when I say volatile liquids, both solute as well as solvent is volatile. Now let's discuss what is the statement of Raoult's law. This is the statement. According to Raoult's law, for a solution of volatile liquid, the partial vapor pressure of each component in solution is directly proportional to its mole fraction. I'll say the statement again. For a solution of volatile liquid, the partial vapor pressure of each component in solution is directly proportional to its mole fraction. So, we can write the expression, the partial vapor pressure of each component, means we have two components, solvent and solute, and both are volatile in nature. So, solvent will have its vapor pressure and solute will have its vapor pressure. So, according to Raoult's law, the partial vapor pressure of each component, so partial vapor pressure of solvent is one component denoted by Pa, is proportional to its mole fraction XA. And the second component is solute. So partial vapor pressure of solute is proportional to mole fraction XB. Now removing the proportionality sign, Pa is equal to P naught A into XA. and PB is equal to P naught B into XB. Now, PA and PB are the partial vapor pressure of components A and B. Partial vapor pressure. XA, XB is the mole fraction of components A and B. Now, P naught A and P naught B. This is the vapor pressure of components A and B in pure state. Vapor pressure of A and B, that is solvent and solute, in pure state. What's the meaning of that? Vapor pressure of A and B in pure state. Pure state means, suppose we have only solvent A. Then we have the vapor pressure only from A. So that is the vapor pressure of pure solvent, denoted by P naught A. And we have the solute B. Suppose we have only solute B, then we have the vapor pressure from solute B, that is the pure solute B. So we have the vapor pressure denoted by P naught B. So P naught A and P naught B is the vapor pressure of A and B in pure state. Means only when A is present, we denote the vapor pressure of A as P naught A. Only when B is present, we denote the vapor pressure as P naught B. When both are mixed, A and B, we get solution. So we get the partial vapor pressure PA, PB. Okay. Now, you know that according to Dalton's law of partial pressure, the total vapor pressure of the solution will be P total. P total represents the total vapor pressure. So the total vapor pressure of the solution will be sum of partial pressures, PA plus PB. Now let's substitute for PA and PB from this expression. We know that according to Raoult's law, PA is equal to P naught A into XA and PB is equal to P naught B into XB. So I'm going to substitute in P total, PA plus PB, P naught A XA plus P naught B XB. So this is equal to P naught A XA plus P naught B XB. Now, we know that for a binary solution, for binary solutions, XA plus XB is equal to 1. Therefore, from this, XA is equal to 1 minus XB. Now, I am going to substitute XA is equal to 1 minus XB in this expression. Suppose I give this equation number 1 and equation number 2. Substituting 2 in equation 1, we have P total is equal to P naught A into 1 minus XB plus P naught B into XB. Now, removing the bracket, equal to P naught A minus P naught A into XB plus P naught B into XB. Or I can write this as P total is equal to P naught A plus P naught B minus P naught A into XB. Now I am going to give this equation number 3. So I get an equation like this for P total. P total is equal to P naught A plus P naught B minus P naught A into XB. Now I am going to make two conclusions from this equation number 3. The first conclusion is that the total vapor pressure of the solution will depend upon the mole fraction of any one component present in solution. The total vapor pressure of the solution, when I say solution, there is solute plus solvent, that will depend upon the mole fraction of any one component present in the solution. That is, it depends upon the mole fraction of the solute or the solvent. Now, on which component it depends, that is the total vapor pressure depends, is decided by the volatile nature of the component. So, when you look at this expression, equation number 3, you can see that we have the mole fraction of solute here, XB. So, according to this expression, I can say the total vapor pressure of this solution depends upon the mole fraction of the component B, which means component B is more volatile than component A. Means in this case the solute is more volatile than component A or the solvent A. Now I can also write the expression for P total in terms of XA. In that case the formula will be P total is equal to P naught B plus P naught A minus P naught B into XA. Now if you look at this expression, you can see the total vapor pressure depends upon the mole fraction of component A, which means that component A is more volatile than component B. So that is the first conclusion about the vapor pressure of the solution. That is, the total vapor pressure of a solution will depend upon the mole fraction of the component that is more volatile. Now, the second conclusion is that the vapor pressure varies linearly with the mole fraction of the component that is more volatile. That is our Raoult's law. That is, vapor pressure is directly proportional to mole fraction. Means as vapor pressure increases, mole fraction increases. That is, the vapor pressure varies linearly with mole fraction of the component, and that is it varies with the component that is more volatile. Now, next we are going to discuss the graphical representation of Raoult's law for a volatile liquid. So next is graphical representation of Raoult's law. For volatile solute or volatile liquid. Now we are going to plot a graph. Now both the graph is between vapor pressure and mole fraction. So this is the graph for Raoult's law. Vapor pressure against mole fraction is plotted, and we know according to Raoult's law the vapor pressure of each component is directly proportional to mole fraction. So we are going to draw the variation of vapor pressure with mole fraction for both the components, that is solute and solvent, in the same graph. Now suppose we have the solvent A. Now we know that in the beginning, the mole fraction of solvent A, XA, will be equal to 0. Now, the solvent will start changing into vapor state. So, the vapor pressure increases, and it reaches a maximum here, where we have the mole fraction of solvent A equal to 1. We know that the maximum value for mole fraction is 1. And when XA is equal to 1, we have the vapor pressure of solvent A as P naught A, because we know that according to Raoult's law, PA is equal to P naught A into XA. Now, when XA is equal to 0, we have PA is equal to 0. And when XA is equal to 1, we have PA is equal to P naught A. This is when XA is equal to 1, and this is when XA is equal to 0. So you can see if there is only solvent present, then mole fraction XA is equal to 0. It increases and the vapor pressure reaches a maximum where the value is P0A when the mole fraction is equal to 1. Now let's represent this as line number 1. And this is the line for the partial variation of vapor pressure PA with mole fraction for solvent A. That is line 1. Now suppose we have here the solute B. Now in the beginning XB will be equal to 0. Mole fraction of solute is 0. Now the solute will become vaporized and vapor pressure increases, reaches a maximum, and here we have the maximum value of vapor pressure as P0B, where we have the mole fraction is equal to 1. So this line, that is line number 2, represents the variation in vapor pressure with mole fraction for component B. And the maximum value of mole fraction XB is equal to 1. When XB is equal to 1, we have PB is equal to P0B. When XB is equal to 1. And XB is equal to 0 when PB is equal to 0. XB is equal to 0. Okay, so this is the line, or the line number 2 represents variation of vapor pressure with mole fraction for component 2. Now the point where these two lines meet, we have here the XA plus XB is equal to 1. And the total vapor pressure of the solution is denoted by this solid line, that is line number 3. This represents P total, which is equal to PA plus PB. And this is our line PB. This line number 2 is PB, and line number 3 represents the total pressure, which is given by PA plus PB. And you can see that in the graph, the maximum value of total vapor pressure, P total, is P0B and minimum value is P0A. You can see this is little slanted line. So the maximum value is P0B and minimum value is P0A. And when you look at this graph, you can see the solute B is more volatile. That is why we are getting more vapor pressure. So the mole fraction will be, XB will be in this direction and XA will be in this direction, the graph when we drew. Okay, so by looking at the graph, we can see that the component B is more volatile than component A. So the maximum value of P total is P0B and minimum value is P0A. So this is the graph for Raoult's law for a volatile liquid, means when both solute as well as solvent is volatile. Now next we are going to discuss about the expression. We are going to find an expression to find the mole fraction of component in vapor state. So next is an expression to find mole fraction of components. Components means solute and solvent in vapor phase. Now you know that in liquid solutions we represent mole fraction with XA and XB. So let's represent the mole fraction of solute and solvent in vapor phase with YA and YB. So YA and YB represents the mole fraction of solvent A and solute B in vapor state. And let PA and PB be their partial pressures. So according to Raoult's law, we can say PA is equal to P0A into YA and PB is equal to P naught B into YB. Instead of XA and XB, we wrote YA and YB. YA and YB are the mole fraction of solute and solvent in vapor state. Now, substituting for YA and YB, we have YA is equal to, YA means mole fraction of solvent in vapor state. YA is equal to, now when you write the expression for XA, we write it as Na, number of moles of solvent by total number of moles of all the components. Now here we cannot consider number of moles because it is in vapor state. So we have to consider the partial pressure. So YA will be equal to PA divided by PA plus PB. Or we can write this as YA is equal to YA is equal to PA divided by P total. PA plus PB is P total. Or we can say PA is equal to YA into P total. So you can use this expression to find the partial pressure of solvent A in vapor state. That is YA into P total. YA is the mole fraction of solvent in vapor state and P total is the total vapor pressure of the solution. Now same way we can get an expression for PB also. Here YB, substituting for YB will be equal to PB divided by PA plus PB. Or YB is equal to PB divided by P total. Or PB is equal to YB into P total. So same way we can get an expression for partial pressure of B in vapor state if you know the mole fraction of component B in vapor state and total vapor pressure. So this is the expression to find the composition or mole fraction of components in vapor state. That is PA is equal to YA into P total. From this you can find YA, PA by P total, and PB is equal to YB into P total. Now next let's discuss the similarity and difference between Raoult's law and Henry's law. Raoult's law and Henry's law. We know that according to Henry's law, partial pressure of a gas in vapor phase is equal to KH into mole fraction. Or Henry's law. This is Henry's law. Henry's law states that the partial pressure of a gas in vapor phase is directly proportional to mole fraction. So PA is equal to KH into XA. And according to Raoult's law, the partial pressure of a component in liquid state is directly proportional to its mole fraction. So the expression for Raoult's law is PA is equal to P naught A into XA. This is our Raoult's law. Now, what is the similarity between Henry's law and Raoult's law? In both the cases, in Henry's law and Raoult's law, the vapor pressure is directly proportional to mole fraction. This is the similarity between Raoult's law and Henry's law. Now, the difference is they differ by the proportionality constant. That is, KH is for Henry's law and Raoult's law it is P naught A. So they differ by proportionality constants. For Henry's law it is KH and Raoult's law it is P naught A. Also we can say that Raoult's law is a special case of Henry's law. So this is asked for exam. When will Raoult's law become a special case of Henry's law? Raoult's law become a special case of Henry's law when P naught A is equal to KH. Raoult's law become a special case of Henry's law in which P naught A is equal to KH. So this is the difference and similarity between Raoult's law and Henry's law, and Raoult's law become a special case of Henry's law in which P naught A is equal to KH, or KH becomes equal to P naught A. Now next we are going to discuss Raoult's law for non-volatile solute. So next heading is Raoult's law for non-volatile solute. Now, in this case, this is also for solutions, liquid solutions, which means our solvent is the liquid, but the solute added is a solid and it is non-volatile. Now, if we have only the solvent with us, for example, suppose I am taking a solvent, closed container, I am taking the solvent. This is only solvent taken, that is A. Now you know that the surface will be occupied by solvent molecules. Now the solvent molecules will escape into vapor state and we get the vapor pressure exerted by solvent denoted by PA. Now, suppose I add a non-volatile solute to this. So, I am going to show another closed container in which I have the solvent. Now, to this I am going to add a non-volatile solute. So, I have on the surface solvent molecules and I added non-volatile solute to this. So, solute is denoted by blue color. Now, the solute will also occupy some of the surfaces here, which means some places that was occupied by the solvent is taken up by solute. But we know that the solute particles are non-volatile. So what happens? The number of solvent molecules that go into vapor state decreases. Number of solvent molecules that goes into vapor state decreases. So this is now a solution. Solution means we have the solvent plus solute inside this container. So this is a solution. So we can see that whose vapor pressure is higher. This is the vapor pressure due to solvent alone. You can see more number of vapors are present. So the vapor pressure will be higher in this container. And here the number of solvent molecules in vapor state is less, because some of the positions of the solvent molecules are occupied by solute particles which are non-volatile. So the vapor pressure of the solution will be less. So we know that when we compare the vapor pressure of a pure solvent and solution, we can say that the vapor pressure of solution which has a non-volatile solute in it is lower than the vapor pressure of pure solvent, or vapor pressure of pure solvent will be greater than vapor pressure of solution. So we know that according to Raoult's law, the vapor pressure is directly proportional to mole fraction of the components, each component. But we know that in this case our solute is non-volatile. So in this case the vapor pressure will depend, vapor pressure means here we have the vapor pressure only to solvent A, will depend only on the mole fraction of solvent. Or we can say PA is equal to P naught A into XA. We cannot write here PB is equal to P naught B into XB. because a solute added is a non-volatile solute. So from this expression we can predict or we can state the Raoult's law for non-volatile solute. Now the statement is this: Raoult's law for non-volatile solute can be stated as the vapor pressure of a solution containing non-volatile solute is equal to the product of vapor pressure of pure solvent and its mole fraction. So that is the statement of Raoult's law for a non-volatile solute. What is the statement? The vapor pressure of a solution containing non-volatile solute, that is PA, is equal to the product of vapor pressure of pure component A and its mole fraction XA. Now, if we plot a graph, so next we are going to discuss the graphical representation of Raoult's law for non-volatile solute. So next is graph of Raoult's law for non-volatile solute. Now again, the graph is between vapor pressure, and here we know that we need to show only the mole fraction of solvent, so XA. Now we know that XA, in the beginning the value of XA, mole fraction of solvent, is equal to 0. Now vapor pressure increases and it reaches a maximum, that is P0A, where we have XA, mole fraction, equal to 1. Or we can say that in this graph, the vapor pressure varies linearly with the mole fraction of the solvent A, because only solvent A is volatile. So this is the Raoult's law for solution containing non-volatile solute and the graphical representation of Raoult's law. Thank you.